Right. So yesterday, asymmetric encryption. So started from the pre-quantum asymmetric assumptions, RSA, elliptic curves, or anyway prime order groups, which can be over finite fields or elliptic curves. And then we build key exchange over it, and using key exchange, we build everything else, because once we can exchange a key over a untrusted channel, we can use it for symmetric encryption, and then we're golden. But we left an authentication shaped hole in the design. Generally, we want key exchanges to be ephemeral, because we don't want a compromise that happens next year to recover all of the keys that were used for the connections over the past year. So if you do authentication by using the key exchange, that means that your public key in the key exchange, the G to the X that you publish, has to stay fixed, because it's your long-term identity. And for example, your long-term identity might be posted on the bulletin board of the university, for example, right? Now, what's the problem with that? The problem with that is that now that G to the X stays the same for a year, that means that X stays the same for a year. And if X stays the same for a year, if in a year somebody compromises that X in the G to the X of Diffie-Hellman, now they can go back and recover the key from the key exchange of every connection from the past year. So generally, we do ephemeral key exchanges these days. And you'll see that referred to as perfect forward secrecy or forward secrecy or future secrecy sometimes. Right. Maybe we should close the door so that I don't lose. Right. So how do we do authentication then? How do we use something that is known to the other party to prove that they're communicating with us specifically? Or in a different setting, how do we sign a document with a digital signature? Say that you're trying to sign a contract and you want to have a public and private key pair, where the public one is known to people as being you, and the private one is only known to you, and it lets you make a signature, just like only you can draw your signature in theory. And anybody can check that signature over that document using the public key. That is the tool of digital signatures. Digital signatures are the other main asymmetric cryptography tool shape, and they let us do that. They let us have a public and a private key, and the private key can produce a signature over a message, which can be verified with the public key. So there are two functions: sign, which takes a private key, well, three, key generate, which produces a private and a public key, which are paired. Then there's sign, which will take a message and a private key and produce a signature. And there is verify, which takes a public key, a message, and a signature, and it returns a Boolean, yes or no. Right? Is the signature valid? Is it not valid? Verify is a completely public function. There are no secret inputs to verify. Verify is done by the verifier who is deciding whether to trust something or not. While sign requires the secret key. Does it make sense what this is for? Like, for example, we can use it to sign a document, but we can also use it to authenticate a key exchange, because you can pick a random X for that specific connection, produce the G to the X of the key exchange, and then make a signature over G to the X, where G to the X is the message, and sign it with your private key. And then this way, when I connect to you, I know that there wasn't someone in the middle who is doing that man-in-the-middle attack that we discussed yesterday. Does that make
my public key?
Say again?
Where am I?
Where do I put your public key? That is the million-dollar question. One way to think about cryptography is that it's a tool that changes secret management problems into key management problems. And yes, that is the practicality problem of this in general. I'll start by giving you like some intuitive, easy cases. You are Apple. You want your phones to only install updates if they come from you. The public key, when you make the phone, you put it into the phone. Easy, right? Before you sell it to me, you put the public key inside the phone so that the phone will check the signature over a hash of the software update before it installs the software update. Now, only the manufacturer, only Apple, can sign new software updates that will get installed by the phone, but everybody's phone already has the public key. That's the easy case.
But this goes against the fact that I want to change frequently.
You want to change frequently the key exchange key because that has retroactive effects. So if you're using G to the X, always the same in Diffie-Hellman, and I compromise X today, and you use G to the X yesterday, I go back and decrypt your connection from yesterday, which I recorded encrypted. Bad. Because now that X is a very valuable target because I can go back and compromise a year of past connections, for example. With signatures, there's no retroactive effect. If I compromise your private key today, I can't send a signature back in time to make you install a software update yesterday because of the time moves forward. So it is still bad because I can make you install something wrong today, but maybe you have a revocation mechanism, and then that's a whole entire field, basically. But this is just reducing the blast radius of compromise of a long-term identity. So your public key becomes your long-term identity, and long-term identities are dangerous. And depending on your threat model, you will want shorter-term identities or not. For example, a very popular tool of cryptography in the 90s and early 2000s was PGP, GPG. And its entire key story was built around long-term identities in a way that I'm not a big fan of, because if you keep the same key for many years, then the security of that key is the lowest common denominator of the security practices you've held for those years. So ideally, you want a system that is indeed more fluid, but it really depends on what setting you're operating in. If you're Apple, for example, no, your phones need a long-term key for you, because somebody might just put an iPhone in a drawer and take it out in 2 years and want to software update it, right? If your key has changed, what happens? You have to keep it. And so, those are probably some of the best guarded keys in the world. Yeah, almost certainly. Because then if you have one very important key, you guard it very well. That's one end of the spectrum. The other end of the spectrum is like Signal and WhatsApp. When you start a conversation with someone, the keys get exchanged right then. And then you can go into the settings to see the key of, the hash of the key of the other person. And if you want, you can compare it with the other person. And if you do that, then you will get warned if the key changes. But otherwise, if somebody loses their phone and needs to change their key, Signal would just go like, okay, the key has changed. It'll warn you with a little balloon. All of these are really hard. Like, if this sounds like a unsatisfactory answer, is because this entire field is made of trade-offs. Because, for example, I just glossed over shows a little balloon. Users do not look at balloons. So usually when you're resorting to telling the user about something cryptographic, you've already lost. And there's a whole thing called key transparency, which makes it a lot better for things like Signal, which is a technology I believe in a lot, and it's about half of what I work on. But that's a whole. The idea of key transparency is that there's a public registry of keys bound to phone numbers, for example, so that if there is a key for your phone number that you didn't publish, you will see it in the registry and say, hey, wait, I didn't put that there. Anyway, there's a whole, and in the middle, there's what we usually call PKI, public key infrastructure. So a PKI is a hierarchical structure where your phone has, your laptop have the public keys of a few trusted entities, usually called certification authorities. Say there's 40 of them. And these are 40 entities which are trusted to check that, for example, a certain website is actually owned by who says owns it. And they can prove it in automated ways, in certain ways. So I want you to know my public key for my website. What do? I prove that I control that website to a certification authority, and they use their private key to sign my public key, and we make a chain. And then when you connect to me, I tell you, okay, so here's my public key, but you have no reason to trust it, right? So here's a signature from a CA, which you do trust, over my public key and my name and my website name, so that you know that they vouch for my public key. And this is the concept of hierarchical PKIs. That is also these days incredibly complex because it is what most of online commerce rests on in terms of security, because without that, you could just intercept a connection and pretend to be a website and do whatever you want. And in the early 2000s, that's kind of how it worked. And yeah, that was great. So there's a whole set of other things that happen, again, public registries of all of the certificates, transparency, and so on and so forth. My company does one of these things, like one of the keys in your laptops is from my company. And and how are those keys distributed? It startles all the way down. Chrome has the public key of Google. And when Google wants to update the list of CAs, they sign it with their public key, which they send down together with a software update. How did you get Google's public key? You connected to google.com/Chrome to install Chrome, right? How did you get that? Well, that was signed by a CA. It startles all the way down. It's generally, it works, like empirically. It's not easy to just man in the middle of a website, so it generally works. But yes, key management and key distribution are the hard problem of cryptography. And you'll hear this a lot, sometimes in a way that grates me a little, because like theoretical cryptographers will be like, oh yeah, key distribution is so hard, haha, and then hand wave it, and then focus on like the little box, and that tends to not work. Like effective cryptography is when you keep in mind the whole system and whether that will actually work in the real world with the threat model and the risk and the key distribution and the human components of the system, and you can expect it to. And a common example is people keep reinventing systems which require lots of people to have their own public key and private key and keep it safe. That just doesn't happen. Like, people cannot long-term keep a key. If you design a system that is based on, well, but these are not like ordinary people. We will make software, open source software authors just have a private key so that they can sign their updates so that nobody can publish a fake update of their software. That sounds good, right? It's important that software comes from the right authors. They will lose the key. What do you do if they lose the key? If you don't have an answer, it doesn't matter what you built. You don't have an answer for how it gets deployed, it does not get deployed, because then the gating deployment on large systems, there are people like me whose job is to ask the question, and what happens if they lose the key? And when you don't have an answer, we basically tune you out. And it's unfortunate because these are smart people that could be contributing to the field, and they very regularly come to us with things like, oh yeah, they're just, we're gonna put their key on a YubiKey, which are these hardless things like this. And that's how they're not gonna lose it. Really? Your mental model for keys is that for keychains is that you don't lose them? Okay. Well, they do backups, right? Right. Nobody ever lost a backup. Correct. Sure. So yeah, they're very hard problem, holistic problem, and in a way social problem too. Like another common one is that passwords suck, and people forget their passwords all the time. And if you and keys are even worse because they can't remember them. So anyway, very big hard problem. Let's now go focus again for a minute on how these things work, but we can scale back out next week, which I kept entirely to talk about protocols and then the realities of getting things into the world. Okay, so how do we do a signature? Let's very briefly look at the RSA and the elliptic curve ones, partially because the elliptic curve ones are not that different from how we do the lattice ones, and they're a little simpler, so we can start there. Let's go back to RSA, which, if you remember, is just that. Nothing particularly special about it. Can you think how to do a signature out of that? So as a reminder, this is the public key, and it's the product of two prime numbers. This is public or fixed, better. And this is the secret private key that you can only compute if you know the prime factors of n. How we do encryption or key encapsulation is that we either make X a message or a random key, and then we exponentiate it to E, and we send that over, and only whoever knows D can decrypt it. Can you imagine how to do a signature out of that?
Well, we
Yes, exactly.
the
Yep. RSA, the nomenclature I like is that RSA has a private operation and a public operation. If you want to do encryption, the sender does the public operation and you do the private operation to get back to what the sender sent. If you're doing a signature, you invert, you publish, you make X your message, and you publish N to the D publicly, and whoever has N can do the thing you published to the E and check what it comes out to. And the thing that it comes out to is the thing you're signing. And only you can make a value that when exponentiated to E comes out to N. So we build a signature primitive because only you with the private key can generate the signature, and anybody with the public key can check that it was correct. Cool. As usual with RSA, there are 15 different ways to do this, because again, the whole game with number theoretical stuff like this is, okay, but how do we turn the message into a number, modulo n, into an x? And again, this is extremely path dependent. The old way is to use PKCS 1 version 1.5, the same of the encryption stuff, the same of the very broken encryption stuff. The signature stuff is less broken unless you fuck it up. So a common way to fuck it up is that you can be tempted to do two things to check a signature. So you receive X to the D, and you want to check if when you do it to the E, it contains the thing that you expect. Now, X has a fixed size. So first question is, how do you sign a thing that's bigger than N? You have the tools. Which tool do you use? That's going to be sketchy because there are a lot of things that are easy to collide into the same value.
Then you go hash.
Correct. So you take a hash of the thing you're trying to sign, whether that is G to the X, whether that is a document, whether that is somebody else's public key, whatever you're signing, you hash it. Great. Now that you have a hash, you can encode it some way in a number. And just consider the number as a sequence of bits, and that's it. So when you do your S, where S is X to the D signature, S to the E, now you're going to be tempted to parse it, because now you have a bunch of bits. And if the rule was, for example, I don't know, you put a 0 byte and a 1 byte, then all 0 bytes, then the name of the hash, and then the hash, which is approximately how PCCS 1.5 looks like, you'll be tempted to scan and parse it, do a parse operation. That is dangerous as hell, because if you get the parsing even a little wrong, then you might skip over some garbage. And if you skip over some garbage, now the problem is not making a value that when exponentiated comes out to exactly the right value, which is impossible. The game now is making a value that when exponentiated has the right high order bits and the right low order bits. That's much easier. You can do that with like a bit of paper arithmetic. And that broke so much stuff. This is an attack that Daniel Bleckenbacher came up with in 2006. And I was finding it in the wild as of like 2016. So it just kept they just kept coming, and there's an explanation of it in this article, so I'm going to just link it in the notes. Anyway, why am I taking this whole side quest? Because I want to mention that every time that you can do something safer, you should. What is the safer alternative to parsing the thing? You know what it should come out to. You have the message when you're verifying the signature. You know the algorithm. You know the hash function. So you, instead of parsing the thing that the attacker sent you and hope that you parse it right, you can just recompute it. You go like, if I was signing this, what value X would I be signing? And then you just do equal, equal. That is not going to break, because then the value has to be that one number. And the only way to generate that exact X when exponentiated to the D and to the E is to know D. So
the private key attached to encrypt it?
No, so you don't recompute X to the D. That's impossible. You still take X to the D and do it to the E. So now you have X. X is just public. X is just an encoding of the hash of the message. That you don't need the private key to recompute it. So instead of parsing X, what you do is you say, okay, which X do I expect if this is a valid signature? You compute X1, and then you do X1 equal X. And you go, and you don't end up introducing these attacks. I'm going to link it. It's pretty fun. But the main reason I was harping on that is two things. Well, one is if you do this safely, that doesn't happen. And two, it is also a matter of fixing parameters, because there are parameters that are not vulnerable to this, and there are parameters that are vulnerable to this. Because it's very easy to do cube roots, approximate cube roots in module 1. Anyway, you can read this if you're curious. Okay, so we built a signature out of RSA. I took a bit of a detour into the attacks, but generally you don't need to know that much about them, because RSA signatures were already kind of on the way out, whichever kind, because of elliptic curves, and now they're not post-quantum. So, right. There are two other ways to do RSA signatures. One is much simpler, but had weaker proofs. The other one is way too complex and probably caused a lot of damage by having completely unparameterized rules. Like, it was defined as just, oh yeah, you need two hashes. They can be different. Why would they be different? If you're using a hash function, why would you use two different ones in the same signature? But yeah, sure, fuck it, why not? And then, oh, you need a mask function. We should make that one parameterizable too. RSA PSS is, there's a colleague I trust very much who traces a lot of the problems of cryptography libraries to that one algorithm was not parameterized well, did not have fixed parameters, and that caused a Cambrian explosion of parameterization in APIs, and that led to a lot of real-world practical problems. I'm not sure I see that lineage myself of issues, but I trust him very much. So yes, again, what happens when you don't just pick one answer for the damn thing? You write the paper and you make it as general as you want, and then you write the spec in which you say, so that can be any number. So it's going to be this number. Okay, just pick it. Anyway. All right. Elliptic curves. How do we do a signature over an elliptic curve? Two main ways, ECDSA and Schnorr. I'm going to tell you about Schnorr because it's the reasonable, intuitive, nice one that is also used in MLDSA in a sense. Well, not Schnorr, but the Fierschemier. Anyway, why does ECDSA exist and why is it more popular? Patents. Schnorr came up with this and patented it. And so they had to go around the patent. And to go around the patent for something that just makes sense, which is the reasonable way to do a thing, you have to do stupid, unreasonable shit. And that's how we got ECDSA. And ECDSA does horrible things like take a value, which is a curve point, which is a x and a y in a field, in a prime order field, and chop it off, take x, then reduce x modulo the order of the elliptic curve group, which has no mathematical relation with the group over which, the field over which the coordinates are on. Like these are two different layer things. You have the field over which the coordinates live, then you do the elliptic curve equation over that. Then that has points. Points, you define addition. Now that you have addition and points, you have a group, and then that group has an order. That order has nothing to do with the field at the bottom. And they just take a coordinate from there, reduce it modulo this, and say, yeah, probably good enough. That drove theoretical cryptographers mad for 20 years trying to prove it was secure. There is sort of a proof in a slightly uncomfortably generalized concept of groups. But we had to do that because there was a patent on the nice, clean, normal thing. But we're going to only look at the nice, clean, neat thing. I just wanted you to be aware of the letters ECDSA, because that is actually the more popular one, which does that silly trick to do patent bypass.
Does anybody actually use
Yes. So yes, there is signature algorithm called EDDSA, which was designed by a group of cryptographers after, including main one being Daniel Bernstein, after the patent expired in, I want to say the late 2000s, and it's seen adoption kind of partial. Like hardware things like this one, for the longest time, only supported ECDSA because there was just not a lot of incentive to update. The incentive to update comes from some practical choices that are not actually tied to the Schnorr versus DSA stuff, which are the kind of stuff that we learned how to do engineeringly better over time. And we're going to talk about it, like how you generate randomness after the break. Yeah, it has adoption. It's kind of flop. For example, website certificates The publicly trusted ones don't use this. They use the CDSA. But software releases for Go, they use this. It kind of depends on when the thing was created. If it was created after the patent expired and after that this was specified, then they tend to use this. Unless they needed to use hardware that didn't support it, because hardware cycles are like 15 years. Because it has to be designed, then manufactured, then shipped, then used. And yeah, you have to work with whatever hardware you have. Also, these days, the difference in security is not that big because we learned how to retrofit a lot of the nice things of the specification of this onto the old thing. The old thing still has that horrible hack, but turns out that's not a big part of why that specification was bad. A lot of it was practicalities that over time we learned how to do correctly in both cases. And I have a lot of opinions on this, and I wrote specs around it, and now it's all useless because maybe quantum computers. So, side. Anyway, let's look at it because it's nice, it's clean, and it helps us then understand the lattice ones. On the left, there is a different thing. This is not a signature algorithm. This is an interactive zero-knowledge proof of knowledge of something. The prover knows a secret scalar, a secret number, x. We are trying to design a protocol by which the prover can prove it knows x, x such that then x times g, remember g, the generator point of the curve, which is just a fixed parameter of the curve. It's just a fixed point. And g times x is that scalar multiplication that we talked about, and a is the product x times g. So the prover knows x and wants to prove that they know x to the verifier without disclosing x, because here x is the private key and a is the public key. Is it clear what we're trying to do? The verifier knows a, and you can imagine this as a asymmetric cryptography door knock thing, where, you know, when the movies, they knock on the secret door and they are asked password, and they have to say the password, right? That one has obvious security vulnerability in that now the person behind the door also knows the password and can pretend to be that person, right? That it's a shared secret. It would be nicer if the person who's knocking knew a private key and the person behind the door knew their public key. And there was a protocol by which they could prove that they know the private key corresponding to the public key without telling them the private key. Does the setting make sense? That's what the interactive Schnorr lets us do. So it works like this. The prover picks a random R value. That's just a random value drawn from a random number generator. And then they do R times G. And that's called the commitment. They send that point over to the verifier. They have to send it before the verifier picks C, because it's important that they can't make R depend on the challenge. Otherwise, they can more easily forge things. Then the verifier also picks a random number and tells the random number to the prover. Yes.
Sorry, I don't understand why you have to pick the random number before or after. I mean, if it's a random number, it's a random number.
It's a matter of pre-commitment. Just like there's a difference between CPA and CCA, the difference is, are you allowed to pick R, a capital R, with the knowledge of C? If you can, I don't remember the math exactly. I would have to do it with a pen and paper, but if you can choose R based on C, so use C in your calculation of R, then you don't actually need to know the secret value to make this equation work out.
Yeah, I think
Okay. Makes sense? So it's just a matter of pre-commitment. It's a malleability problem. If you need to not be able to change your mind about what the R value is after you've seen what the other party's challenge is. So the other party selects a random C, completely random, and they send it to you. Now you do this. This is a simple operation. You take their value, you multiply it by your secret key, and then you add the commitment R. You send that over, that's your response. The verifier can verify this equation. And if you expand S here, you'll see that R times G is capital R. C times X times G is going to be C times A, because A is X times G. So this equation verifies. Make sense? The only way you could have made a S value that makes this verify is by knowing the X value that, when multiplied by G, makes A. Otherwise, there would have been no way for you to know how to make that equation balance. So makes sense how this makes a interactive protocol. How do we turn this into a signature, though? Because in a signature, we don't have the other party to talk to. We're just trying to produce a value offline. There's a single arrow. It's called the Fiat-Shamir transform. The Fiat-Shamir transform is a heuristic you can apply to challenge response protocol to turn it into a non-interactive protocol. And there's a single trick to it. And the trick is that you make the challenge C, instead of being something selected by the other party, you make it a hash invocation over everything that you've selected up to that point. Why a hash invocation? Because the hash invocation is that random oracle model where it's as uniformly distributed as a random value, and you don't get to control the output. So you can't make it have the exact value that you would need to fake the signature. So instead of sending the commitment over to someone and waiting for them to select a random challenge, you make the challenge the hash of the R, the capital R, because the other side needs to know how to compute the challenge then, the public key, and now you can add a message to it. Because we can put it inside the challenge. Here, the other side could also have put a message inside the challenge to check that you were effectively signing it, but this is an interactive protocol, so it didn't matter that much. But with signatures, we are signing something. We're signing the hash of something. And so now we can put the message, whether that's your DocuSign document, your the public key of someone you're signing, a G to the X, whatever it is that you are trying to make a digital signature over, you put it inside the challenge, inside the hash that becomes the challenge in the Schnorr signature now. So the Fiat-Shamir transform takes an interactive Schnorr protocol and turns it into a Schnorr signature. And that's the only thing that changes, really. At the top, you see R not computed randomly, but instead computed as a hash. That we can talk about after the break. Pretend that's still random. That's not part of the Fiat-Shamir. That's part of the ED25519 design. So really, the only thing that changes from left to right is that instead of the challenge being picked by the verifier interactively, it's a hash function of commitment, public key, and message. Questions on the break?
Yeah. I don't necessarily like What are like the pros and cons of doing online versus offline signature?
You just can't use an online one for a lot of things. Like online truly requires the other party to be there with you while you are doing the protocol. And imagine DocuSign. You sign something. DocuSign does not actually use digital signatures, but imagine a version of DocuSign that's actually based on private keys. Why is it not based on private keys? Because people can't hold on to their private keys. But anyway, imagine a version of. You want to make the signature at home, right? And then you want to maybe put that in a zip file and email it to someone, right? That's a single arrow. There's only one flow of data. You are making the signature and then you're sending it to someone. There isn't like those are three emails. And most importantly, those are three emails every time somebody wants to check it. Signatures are publicly and offline verifiable. It means that, let's take the Apple case. Apple wants to sign the software update to update iPhones, right? Apple can just make the signature once offline in a probably very well secured environment because you have very secure keys. And then they can take that signature and just distribute it to everybody. The phones don't have to do the whole protocol with Apple, where Apple has to have the key online to respond to the protocol. The signature is the same for everybody, and everybody checks the same signature. They can just post it publicly on a website, which is kind of what happens. The software update is just a thing you download from a website, and you just download it and it works. You can even do things where if you have a school with a lot of MacBooks and you want to update them all without downloading 100 times a software update, this actually exists. You can download the software update once, put it inside the school, and then everybody downloads the software update from inside the school. That wouldn't work with this because this requires talking directly to whoever has the key. There can be no intermediate distributor.
But then, like in this trade-off, you want to say like offline is better than online.
So for the signer, yes, yeah. So these are signatures. These are not even signatures. These are basically not used. Yeah, no, this is interesting because the Fiat-Shamir transform is a useful tool that is used also in MLDSA. So I wanted to show you how it works because it's useful to generally be able to recognize the shape of, oh, this is a challenge computed as a hash from a commitment and a message. It's a useful pattern to be able to catch on to recognize how things work. Because MLDSA does the same thing, but you're just not going to capture this in the wild. The signatures are the thing.
So, but I was wondering, if I adopt the non-interactive version of the rights, I might not supposed to about that. Like once I send a signed message, then someone has to look at the conversation and resend the same authenticated message.
They can, but they cannot change the message.
Yes.
Yes.
But it's still a problem.
Depends.
It's like invest $10 and so on that, and iterate it.
Yes. So that is a very good point, and those are called relay attacks, where somebody can take your message that's signed and send it over to someone else. Those are absolutely real attacks, and depends how you build your protocol. Yeah, everything is about protocols. So, for example, the common way this is used is that instead the thing you sign is not invest $10. The thing you sign usually is key exchange. No, just a key exchange to open a connection, and then over that connection you do you say invest $10, which, however, is online. See, it really depends on the use case. If it's a software update, you're fine with it being rebroadcasted. You want it to be able to be rebroadcasted and relayed. If it's a one-time investment instruction, you want to defend against relay and replay attacks. because a slightly similar version of the attack is I don't send it to someone else, but I send it twice to the same recipient. And those are replay attacks. Those are absolutely real, and you need to design the whole system to be whichever makes sense for what you're trying to do. And there are ways to avoid replay attacks where instead you basically reintroduce this by having the recipient give you a single use value, and then you sign that. But we generally still use signatures because these are well specified. Like we have these as a very well-established building block.
What you mentioned, but one solution would be to use this to set up a key exchange.
Yes,
But key exchange is an interactive protocol. So
correct.
Back to the question again.
I mean, if you don't want replay, you're going to need either interactivity or you're going to need the ability on the recipient to detect replays.
Yes,
so
like I was thinking, what if you require that the message comes with a timestamp, something like that?
Timestamps, sort of.
Timestamps.
No, timestamps are, I mean, this is actually a real problem space that's explored in some protocols. And timestamps help bound the replay attack. They don't help prevent it because things take time to move over the network. So you can't say the timestamp has to have this specific value. You have to say it has to be in this range. And that means that for 50 milliseconds, it can be replayed. And you have, that might or might not work depending on your setting. Another thing you can do is say, every time I sign something, I include a counter, a value in it, 1, 2, 3. And then the recipient, if it sees twice something with the counter 2, it will say, nope, nope. Does that work? Sort of. What if you have 10 machines that are serving responses? Now they have to coordinate to tell each other, hey, by the way, I've seen 2. Don't accept 2 anymore. And you can have races because if they first do the operation and then tell the others, hey, I've just done 2, don't do it. They could, if you send it at the same time to 2 machines, they will both do the transaction for $10, and then they will tell each other, and maybe they'll realize, or maybe not, but anyway, the operation is done by then. So instead, you have to do a 2-step distributed system commitment where they receive something, they take the number, they tell everybody, hey, I am doing 2. Is anybody doing 2? Has anybody already done 2? No? Okay, so 2 is mine. And then they go and do it. What happens is that if that machine crashes or gets separated from the other machines by the network because somebody drives like an excavator machine into the ground and just pulls out the fiber, which happens a lot more than you would think. I mean, fiber just goes under the ground in places and people just excavate places sometimes, and computers just stop being able to talk to each other because now there's no fiber between them. What happens then? That's called a partition. How do you solve that? Well, you can have a group of machines vote with a majority over who is allowed to use 2. It's complicated. Like replay protection is hard. Interactivity kind of solves it for you, but then you need interactivity. Sometimes you want that, sometimes you don't. It gets even more complicated when you start combining it with encryption, because now if you first sign and then encrypt, somebody can decrypt it, keep the signature, and encrypt it to someone else. And but if you do the other way around, where you first encrypt and then sign, now somebody can take off the signature, even if they don't know what's inside and they're not the recipient. Anybody can do it. And then they can put their own signature on it and send it to someone else. Send it to the recipient who can decrypt it. And the recipient will logically think, okay, this person who signed it knows the message, but they don't. They just signed an encrypted thing. So whether you do it first sign then encrypt or first encrypt then sign, you have attacks. There is a thing called sign encryption, which does both at the same time and makes them inseparable. It's basically not implemented anywhere. Yeah.
Should it be implemented?
It's a good question. Yes, probably. Yes, so yes. I get asked this all the damn time because I've developed one of the tools used to encryption things that is most used these days. And it does not do signing because it's fundamentally different UX to know the public key of the persons you are in it's different to need your private key to make a message or to know the public keys of the recipients. Those are different user experiences, like different ways to communicate things. And there should probably be a thing built on top of that that does sign encryption. I just never had time to build it, honestly. There's just as much time in the day. The thing people use to do that sort of thing is PGP or GPG, which is an implementation of PGP. And that does sign then encrypt. So you can do the thing where you decrypt it, keep the signature and encrypt it to someone else and relay it to someone else. There's no reason they do that. They could do it with sign encryption, but GPG has so much stuff that should not look like that. But it was designed in the 90s. Everything can be excused to stuff designed in the 90s. What I don't excuse is still using things designed in the 90s. Like Phil Zimmerman, the author of PGP, told me that he doesn't use it anymore. And there are people who have like an emotional attachment to that thing. So what were we talking about? That we got to the end of this. So we've seen how to make a signature out of interactive protocol, and interactive Schnorr turns into Schnorr signatures, and everybody's happy. Cool. So we need to talk about MLDSA, and then I wanted to talk about some practical concerns of this stuff. So MLDSA, again, module lattices. Again, I am the wrong person to teach you how the actual lattice theory behind it works. But so again, we're going to treat a smaller box as that box that does the thing that we expect. And there is a similar operation you do with linear algebra that looks a little bit like this one. The one difference is that, annoyingly, S, when you're doing the lattice operation equivalent, S leaks bits of X. Now, that's very bad, because S is your public signature, and X is your private key. So that's a problem. So instead, we do a thing called Fiat-Shamir with aborts. What it does is that it does Fiat-Shamir with the challenge and the random stuff and so on. But it then checks whether the vector S, which comes out, is within a number of ranges. If it's within those ranges, then you can prove that it doesn't leak any information about the key. It's within the noise range. So essentially, it tries multiple times to do this with different challenge values until it finds a S value which doesn't leak bits of the private key. Then it publishes that, and we've got a signature out of it. So, yep.
Why does S leak? Like, how does it leak the bits of it? Is it like some mathematical?
It's the mass of it. I think that it's because the high bits of X are the private key, and if the coefficient in the values are vectors of polynomials of each of 256 coefficients in MLDSA.
Values of X.
But all of these values, like instead of being just numbers, they are short vectors of polynomials. And if the The nice thing about MLDSA and MLChem is that you can implement all of it without even thinking about what a polynomial is, because for the implementation purposes, a polynomial is just an array of coefficients. And you just do that, and then you do a number theoretic transform to make multiplication simpler. So you map into the entity domain, do your multiplications, map out of the entity domain, and there's a little nice algorithm for how to map into the domain where multiplication is easier and one to map out, and you don't really have to think about it too hard. But anyway, so going coefficient by coefficient, my understanding is that you leak the high bits if the S is out of range, because the high bits of S will depend on the high bits of the private key. But the low bits instead are hidden by the noise vector you've added. So the thing you do is just you check the infinity norm of the coefficients, and if it's too far from the centered value of the coefficient, you just reject and do it again. On average, you reject, I don't remember, you can calculate how often you reject, and it's reasonable. It makes signing slower, but a little bit slower. It's manageable. What it does make harder is testing whether something is constant time, because now it's definitely not constant time, because it retries and it has what's the distribution? Geometric distribution for timings, because it's just random rejections, repeated random rejections. Yeah, and one thing that makes hard is benchmarking. Like, how long does signing take? Like, depends. Are you lucky? It's very fast. Are you unlucky? It's slow. And if you're trying to make signing faster, you make like some code change, and now you think it's faster. How do you measure it? Before a geometric distribution averages out, it takes a very long time, because you have a lot of variance with a lot of tail values that are very high. So you need to do a lot of tries to average it out. And now you are spending an hour every time you make a change to see if it's faster or not. So I think I did is that I did just the math for what is the average representative distribution of rejections. And then I built a sequence of inputs that does exactly the average representative run. And then I benchmark that deterministically. And that tells me a representative running time for the correct average. Anyway, this is just useful for development. And these are all the implementation concerns that layer on top of all of the math. This is completely removed from the actual security of the lattice math, but it's kind of important because we need to know if it's fast, because we need to know if it's fast enough to do it, 10,000 times per second on a certain machine, or if we need more machines or bigger machines and stuff like that. Right, so the thing that comes out is called MLDSA. MLDSA, like all the good algorithms, is very parameterized, as in rigidly parameterized. And parameter sets there are three parameter sets: MLDSA 44, 65, and 87. I kind of wished I didn't call them those numbers that we just had to memorize, but it's because those are the K and L values, which are the lengths of the vectors. And you operate over a matrix, which is K by L. So either you operate over a matrix that's 4 by 4, 6 by 5, or 8 by 7. And each element in the matrix is a polynomial of 256 coefficients. So the result is that stuff is big. This is the problem with both MLChem and MLDSA, and the reason we weren't using this stuff before we were worried about quantum computers. Elliptic curve signature is 64 bytes. Big, like annoyingly big. And we designed a lot of protocols on the assumption that signatures are small and cheap. And so we were like, oh, we would like to also get this entity to vouch for this or something. Sorry, stick another signature in it. Whatever, it's 64 bytes. there's space. Generally, in a packet, a single packet that goes over the network, you have approximately 1,300 bytes of space. 1,600 bytes of space. So, 64 bytes, whatever, put however many you want. That doesn't fit a single packet at all. And if you put 5 of them, now it doesn't even fit a single round of packets before it needs to slow down and check if the other side received it. And now your phone will take like a second to open a connection to a website, and that's bad. And that's kind of what we're working on right now. Like ways to reduce the number of signatures needed to open a connection from many to a single one by doing more clever things with hash trees and stuff like that. None of it is at the signature level. Signatures, this is what we've got, this is what we've got to work with. But the holistic system, again, we can redesign it with the new constraints in mind. Signatures used to be cheap, so we could just say, oh yeah, just put 5 signatures in. Now signatures are not cheap, so we need to rethink the thing. And I thought we were going to have more time to rethink more protocols, and apparently we don't, because quantum computers might be fun. And so some protocols will just suck a bit because they were designed for small signatures, and now signatures are big. It's an open problem in many things. Small radios have a big problem with this because instead of sending 64 bytes, they're now sending.
But is there any hope of finding
a different signature algorithm that has better? So NIST is doing a second round of signatures, and there's a couple that are interesting. One is unbalanced oil and vinegar. I'm not kidding. There's something about how two things don't mix well, and so they're oil and vinegar, and then unbalanced is a variation of it, whatever, U of V. And the other one is ski sign, which is instead, I think, based on elliptic curve isogenies, but don't quote me on that. They are still very early in the process. So remember that I told you that MLChem was selected with an international selection process that over the years narrowed it down to concentrate more cryptanalysis research on the remaining ones and so on and so forth. Right, they did that and they selected this. They actually selected 3. They selected this, they selected one that is based on hashes, which is actually bigger. Well, the public key is very small, but the signature is way bigger. And that we're more comfortable about because it's based on hashes, so it doesn't have an assumption of lattices or anything. And one that is called Falcon, which has the problem that the verifier is reasonable to implement. By the way, this stuff very easy to implement, easier than RSA and ECDSA. People think that since they're bigger, they might also be more complex and slower. They're actually faster and simpler, but they're bigger. And Falcon is simple to verify, is horribly complicated to sign, like catastrophically complicated to sign. Very difficult to make it constant time. It involves floating point numbers. It's kind of hell. And they didn't actually publish the specification of Falcon yet, which we're not really sure why. When we asked NIST, they just kind of like rolled their eye and say something about the head of the Department of Commerce having to sign off on it and not having signed off on it yet. Now, is it because the US government currently is not very competent, or is it because maybe the NSA has found out something about Falcon and doesn't like it? Who knows? Who the hell knows? So we don't have the spec for Falcon. So these are the ones that actually finished the process. Then they looked at the set and said, well, these are kind of bad. Like, these are all large. Let's do another round, but that will take years. And by now, by the time they get here, it might be too late. And so we kind of have to ship with this. And it's unclear it would be worth it after we ship this to reship a whole new thing, which involves so much work by so many people and so much risk, because you have to write new software and you have to learn how to do it well. And this is simpler. So, the risk I'm reasonably comfortable with, and we've spent a lot of time building test vectors to find all the different ways you could have done it wrong, but still there's work and risk involved, and it's unclear it will be worth it. Just like I remember how there was the Schnorr and DSA, and not a lot of things switched to the new Schnorr signatures after the patent expired. It's because there's a real cost in adopting the new thing, and it needs to be really worth it. And can't predict the future. Maybe, ski sign will get specified in 3 years, and then in 5 we're going to start migrating to it, and then in 10 we'll be using ski sign, but that's in 10 years. So yeah, the speed at which we're deploying this is because we have time pressure. It's not going to happen for the next thing, because by then we'll be like, well, the old thing is secure. This will be a little faster, well, a little smaller. That's nice. So we might get deployed in a few places, and then there will be a little trickle of attention to try to move it to it, but not super convincing. And it's unfortunate. And it's yet another thing that's path dependent. If we had maybe come up with ski sign before all of the other stuff, maybe that's what we will be deploying today, but that's not. Hence. And LDSA is what we got. All right, so yes, right. So we've talked about Fiat-Shamir, we've talked about how it involves some randomness, right? Both R at the top there and R at the top there. Why is the randomness important? If you squint, you can see that if R is the same in 2 different signatures, you can solve for X. If I remember correctly, you do the subtraction between S and S1. Yeah. Okay, I'm not remembering it off the top of my head, but actually it's on the Schnorr. There. What is the notation here? What is E? Oh, E is C in our, yeah. Okay. So this notation uses E instead of C. But if you do if you reuse the same random value twice, then you can just subtract the 2 S commitments. So if we go back to this, oh yeah, sure, okay. If R is the same, if you subtract these 2, R cancels out, right? So now you have the difference between K times A or X, short, and K1 times A. If you want, you can look up the formula, but like the point is you just do the very simple equation and then you solve for X, which is not great. So it's very important that R is different every time you make a signature. And in theory, this is easy, right? You have a random number generator, just take a random number. Practice. This broke so much stuff. The famous one is the PlayStation 3. The software updates for the PlayStation 3 were signed with elliptic curve with ECDSA, which works the same for our purposes. Imagine it was Schnorr. And they used the same random number twice for 2 signatures. And so people just took the 2 signatures, subtracted one from the other, solved for X, and then they proceeded to sign modified operating systems for the PlayStation 3. It was fun. And I mean, that led both to running Linux on it and to piracy because. So this happens all the time. I gave a talk in 2014 about this happening on the Bitcoin blockchain because Bitcoin is just a giant database of signatures where each transaction is signed. And so you can just take all the signatures and look for people that reused the random number and just recover their key and steal their money. We did not steal their money. Their money had already been stolen because people would just detect that happening and steal their money.
How can you detect if someone uses the same?
Look at the signature. The signature is the commitment R, which is small r times G, and S. So if small r is the same, big R is the same. So the first half of the signature is the same. It's actually a lot scarier than that. If there's even a single bit of bias in how you select the R value, you can do lattice attacks to it and recover anyway. That's much harder to notice because then big R will come out different. But if you have a suspicion that that happened, because for example, you look at the software implementation and you're like, aha, they're not selecting it uniformly at random. They have a little bit of bias in their distribution of R's. You can use that bias to extract the key. It's not as easy as doing a subtraction, but.
It's a whole thing, like if the message changes, then R also changes.
Aha! You've spotted the thing that DSA does to avoid that. Notice how here R is random. Over there, it's not random. It's the hash of the message and wait, what? H1. It's actually the hash of the message and the private key. Why the hash of the message and the private key? Because if you hash message and private key, the result will be unpredictable to the attacker because they don't have the private key. And it will be different for every message because you hash the message. So that's exactly what EDDSA did to prevent those attacks.
It was after.
Yes. So remember how I told you, ignore that box at the top. You could pick R at random, but we don't. This is why we don't. Yeah, there you go. So you've seen the. Turns out this is still not the best approach because this still has a problem. What if it has two defects? One of them is that. So here the challenge is the hash of R, A, the public key, and N, the message. R at the top is the hash of the secret key. H1 is the secret key. Is technically it doesn't matter. You can mentally model it as a hash of a secret. And N. What happens if by mistake you mix up the pairing between your public key and your private key? Because you make a software mistake and you think that this is your public key, but actually you've swapped it. And this happened, by the way. And more concretely, this happens when the library asks you, hey, to make a signature, give me both your private key and your public key. And why is it asking you for both? Because it needs the public key to put it in there, into K. And why is it asking for it instead of recomputing it? Because computing it is slow. So the library will ask you, hey, you've stored your private and public key, right? I gave it to you to store somewhere. You stored it safely, right? Good. Give them back to me. What happens if you just make a mistake and give it the wrong public key? What happens? And you sign the same message. Does R change?
Yeah.
No, it does not contain the public key.
I mean, if you put the public key instead of the.
So you make a signature with you sign message M and the message stays the same with your correct private key and public key. So far, so good, right? You've just signed a thing. Great. Then you make a mistake, and you just think that your public key changes. You've stored it in the wrong place, the role of the database gets mixed up, the attacker has the ability to tell you the public key for some reason, there's a software bug, something. And now you sign the same message with the same private key, but a different public key.
Different public key.
Yes.
That's the same.
Yeah. Our state stays the same, but K changes. And you solve for X again. Boom. Sounds far-fetched? It happened. It actually happened.
And so in the blockchain or whatever, you can find people that do this mistake.
Yep. Or you can force them to make that mistake because maybe the software does something silly like letting the attacker select the public key for some reason or whatever without actually checking that they match. There are many ways to make mistakes. But the problem is that you make a little mistake, which is like, oh, I got the wrong public key. And the result is the private key can be recovered from the signature, which is catastrophic. So it would have been a little better to also put A in R at the top. But even better would be to put also some randomness in R. Like the thing we're defending against is what if your random number generator is broken and for some reason produces the same random value twice, which is the mistake the PlayStation did, right?
You can use a counter.
You can use a counter, but you can also say, I want to defend, make this robust against either mistake. If R at the top also contains some randomness, then you would have to get both the wrong public key for the attack to work, and you would have to repeat the randomness. If you did not do those two mistakes at the same time, then you would be safe. Does that make sense? The other reason to put some randomness into H that computes the R value. So what I'm talking about is called hedge signatures, and it means computing R from private key, public key, message, and a random number. You put all of those into the hash, and that's your R value. This is called hedge signatures, and it's what MLDSA does. It has two other advantages. One of them is that the resulting signature is random, so you don't leak whether you're signing the same message twice. Which doesn't matter? Depends. Depends what system you put it in. Like, does it matter that the signature is the same when the message is the same? Maybe. The message might be public, in which case no, because then they can just look at the message and see that it's the same. But sometimes randomized signatures are used. And the other advantage is that you're protecting against mistakes, including mistakes by the computer. Another thing that happens is called fault attacks. Fault attacks are all those attacks where the problem is not the algorithm, but that the algorithm does not get executed correctly. For example, because, and I'm kidding you now, cosmic ray hits your CPU while it's computing. It happens. And if it flips a single bit, what happens if a cosmic ray hits K while you're signing something? You keep signing the same message for some reason. Like you sign, everything is good. Everything is good. Everything is good. Or you sign something that the attacker can control, so they make it always the same message. And then a cosmic ray hits you and changes one bit in K. What just happened?
Will the verifier just not be able to?
Doesn't matter. Because now the attack is against the private key. The verifier is not even in the picture. So what happens is that
just the fact that put R, S, and M out of the wild is a problem.
Yes.
Okay.
Yes, exactly. So if a single bit flips in K, you now have K and K1. So you're going to have S and S1, but they both have R, which is the same.
But I mean, don't you put just one of the two out of the wild?
No, you keep signing and putting them out into the wild in this setting.
Okay.
Because it's safe, right? You're just signing the same message over and over and putting the signature out there. Why would you worry about it, right? Why? Because now a cosmic ray hits your K, and now the single bit means that there's a S and a S1. Then S minus S1, R and R cancel out, but now you have K times A and K1 times A. You move A to the other side, you have the difference between K and K1. Done.
But you still need the division, and it shouldn't be easy to do. Right?
Oh,
because you have to do S minus S prime or like.
no, you can do an inverse. You can do an inverse in the field.
But isn't it like the reason why we use this is because it's hard to do the division?
The division that's hard to do is this one, the scalar, when you do the scalar multiplication by a point. These are just scalars. These are just
by number.
I mean, it's not division because it's in a modular field. But remember that when we were using just plain numbers, we're not using multiplication, we're using exponentiation. The hard thing is the logarithm. Multiplication is trivially invertible. You can calculate the inverse in a field of a number. For example, you can exponentiate to the order of the field minus 2, and that is the inverse in the field. So yeah, it just plops out. So instead, hedged signatures are the ones that pick a random value every time, and then it wouldn't be a problem even if K gets a bit flip from a cosmic ray, because R is different every time. And so there's no problem of R being the same. So those are called hedged signatures, and MLDSA is a hedged design. And you can actually do hedged signatures with ECDSA, even the old one. There's a design which is currently a draft, and the authors tell me that they're not interested in getting it to a final specification, so I just implemented the draft anyway because it's safer. But I mean, it's not moving because the group that does these specifications does not prioritize the things I would prioritize anyway. But it doesn't matter anymore because pre-quantum, so probably not worth the effort anymore. Like MLDSA is hedged, so got that covered. Questions?
It's so like long to read. I mean, I guess all these distribution problem is hard because it's long to implement things in different systems, right? I mean, we just have to implement this key thing in one system. I guess which can be done in one time, right?
What is this key thing? Like the hedged design, or
the key something for another post-quantum algorithm? I don't remember.
Oh, ski sign.
Ski sign. Yeah.
Yes, it's written SQI.
Oh, okay. So it was okay.
Yeah.
Ski. So if it's this hard to implement it, I guess the problem is you have to distribute a lot.
There's so much work, and this is something that again theoreticians miss all the time. So you have to first write the specification. And the specification, everybody has to agree on the specification, and it has to work for many different cases that go from this thing has to know how to make a signature. Like this is a small chip. It has little power, and its thread includes somebody plugs it into a machine and wants to extract the key. So it's trying to convince it to do something silly so that it will leak this. All the way to the servers of Google have to make millions of signatures per second to serve connections. So you have this very wide space. Then that specification has to be put into protocols, because you have to agree how do we even say I'm going to use key sign in TLS. You have to assign a thing called a code point, which are these lists of parameters. like this is the list of signature algorithms that can be used in TLS, and they have numbers so that you can say, I'm using signature number 3, and you know that that's the signature type. Then you have to implement it in the libraries. That's my job. Like somebody has to do the actual implementation, and my job is to implement it in Go, but then there's somebody whose job it will be to implement it in Java, multiple people actually. And then in some C libraries, and then those need to get deployed, and then we need to test whether that works and that has impacts. Chrome needs to start rolling it out. It needs to, but for signatures, it's even more work because now remember that there are those certificate authorities, which are the trusted ones that they have to generate new keys because they need to generate the new keys of that type. And those keys need to be generated on secure hardware machines that where they are stored. And those are called hardware security modules. Those have to be produced and shipped and validated. And there's a certification process for these things that takes years. So they need to get certified. It's called FIPS 140, you don't want to know. And they need to get manufactured, tested, certified, and then the CAs need to buy them. They need to put them into a rack. Then they need to call the auditors to observe them generate the key and attest that they were generated securely without, a paper backup off to the side or stuff like that. But then those keys need to be distributed to Chrome, who needs to distribute them to you. Years. Many years.
So there's no option of doing it once in as you were saying like last week, assembly or whatever, like the core algorithm, and then use.
I mean that only helps with a little bit piece of what I just told you, and generally that will not be an implementation that works for all of the use cases. That there are some people who believe that. And by the way, if you need to go, don't worry about it. All of you just I don't want to run over, but there are people who believe that we could just write it once and use it everywhere. First, that is a small chunk of the problem, and second, it has so many problems. Like Go is nice because it cross compiles, because it uses the same compiler for everything, and so on and so forth. There's just too much reality getting in the way of that. Any other questions? With this, I think we've talked about every core-based primitive of cryptography. So next week we talk about protocols and the realities of putting them together, which is the part I specialize in. So I'll have fun. Cool. Well, see you next week.